Hey everybody, great to see you again. Mr. Smith here. In today's deck, I'm going to explain everything you need to know about projectile motion, but before I do, I want to explain the first word, two-dimensional motion. We've already done this. So there's a key insight that you're going to get from the last topic we did where we added vectors that's going to help you in this one. So let's check this out. If you remember, what we were just working on with vectors was something like this. If I walked 10 meters to the east, and I walked 7 meters to the north, then you can explain to me basically what it was that I did, and we'd say, yeah, this is what you did, your vector R, and yeah, there's something obvious that's built into here. In fact, it's built into our XY coordinate system that we didn't talk about. When you move east, you're not moving north. Think about it. X and Y, because they're perpendicular to each other, are independent of one another. And that little fact turns out to be one of the key insights that Galileo, the granddaddy of modern physics, brought when he cracked this problem. So here's the story. In 1637, Galileo wrote to his friend Diodati in a letter and said, I've solved the problem of projectile motion. So I'll explain why he was concerned with this in class. But projectile motion was basically like this. If you imagine Galileo's got a cannon and he's going to shoot some cannonballs, he realized that if you were shooting really slow cannonballs, you could ignore air resistance. And if you shot a super slow cannonball, it might go like that. If you shot it with a little more oomph, it might follow a trajectory like that. But that idea is common sense. You understand how that works. Things can fall and move to the side at the same time. Okay, so file that away. 50 years later, Isaac Newton published the biggest book in the history of the world to that point about science. It was called the Principia. And what Isaac Newton did was he took Galileo's discovery about projectile motion and extended it one step further. That's just fascinating, and it's also something we could talk about. Here's what Newton did. He drew an image in the Principia, this image right here, of a gigantic mountain, and he could launch projectiles like a cannon from it. This one, D is a lazy one, E is one with more oomph. If you look at when you get letter F, you get a projectile that travels like a quarter of the way around the Earth before it impacts. And the thing was, if you got this projectile going fast enough, you could actually follow a trajectory like this outer one right here. It would curve and curve and curve as it falls towards the Earth, but the Earth was also curving. And what that was all about was the recipe for how you put something in orbit. So what Newton did was to link this stuff with the idea of how the moon actually orbits the Earth. So it's kind of mind-blowing. It's just too cool not to mention. But let's get right to it, and I'll show you everything you need to know right here. To begin with, we've got an image of two balls that are falling. What I've got is a purple one and I've got a yellow one. So the deal is they just let the purple go, they let the yellow go, but they kick the yellow ball at the same time. Now we've got a strobe camera that makes a lot of flashes per second. It's about 0.04 seconds for every one flash. So you can track by lighting the ball up where it is, and the room goes dark in between, so you don't see the balls in between, like here and here, for example. So the thing that I want you to do is to pause the deck and look with your own eyes if you want to. Notice that if we draw some horizontal lines and space them evenly, that these balls, the yellow one and the purple one, they track together perfectly. So what that means is the first discovery that Galileo made, and that was that whether a ball is moving sideways like this one or not, the Y motions of the balls are going to be the same. That's a huge discovery. What he figured out was that the X motion here and the Y motion here are independent, just like we were when we talked about the vectors. The 10 meters and the 7 meters, they're independent if they're east and north. So what we're going to do is to extend this one step further and talk about the other discovery. What I did was I put a bunch of vertical lines on the image, and what they do is they let you track actually the sideways motion of the yellow ball. And here's what I get from it. I get that the yellow ball moves forward the exact same amount every single frame that goes by. And what that means is that because of inertia, which you remember Galileo figured out, because of inertia, the x motion of the yellow ball is constant. All right, so let's put it all together. What you've got is two equations, and I'll give them to you in just a second once I set up what the variables are. So what we're going to talk about is x stuff and y stuff. So I'm going to write a vx up here. It's a velocity, but if you look, it's a velocity in the x direction. This is going to be an up and down distance. So I'm going to call it a d, and it's a y. Because it's a vertical, it's a distance in the y direction. And this distance out here is going to be a d, but it's going to be an x. So what this is all about is if I shoot a cannon or jump off a cliff or throw a thing off a table, what's going to happen is the arc is going to follow some kind of shape like that. It's called a parabola, and it's going to be governed by two equations. First equation is dead simple. dx equals vx times t. That's because the sideways speed of the ball is always the same. It's just constant motion. Then there's the Galileo free fall equation. He figured this one out when he was studying objects, and I will show you in class how this is connected with the equations that we've been using all along. So what this says is the distance y that a ball falls is 1/2 of gravity. Remember, gravity is 10 meters per second, and time squared. Okay? So you got those two equations down. Let me show you how this actually works in a sample example. So example number 1, we've got a diver that leaps from a 10-meter high cliff. So 10 meters, I'm going to snipe that. That's the dy. So I've got dy equals 10 meters. Then they give us the horizontal speed. That's going to be the vx. You notice the x is horizontal. It's going to be 5 meters per second. All right, and finally they're asking how far from the base of the cliff will she land? So what she's going to do is follow that pathway, and she's going to sploosh out here in the water, and we're going to want to find out how far is that. So that's going to be the dx. So just like we've always done all year long, you can say dx equals vx times t is one of our equations, and then we have dy equals 1/2 gt squared, and just go shopping. What can you do? So dx is no good to me because I don't know time, and I don't know the dx. In fact, they're looking for the dx, right? So I only have the vx in this equation. I have to wait to use this one. But that probably means that I'll be able to turn this one around if I want. So dy they do give me. G I always know. It's 10 meters per second squared, and I'll be able to solve this for the t. So what I'm going to do is a little algebra. I solve for the t by multiplying both sides by 2. So that gives me 2 dy. Divide both sides by the g, and then square rooting. So if you follow all those steps, what it looks like is this. 2 dy over g inside the square root symbol gives me the time. That's worth writing down, just like you're going to write down all of it, but that's worth really remembering because it's so common that we use it. So I'm just going to plug in here. So if I've got a 10-meter high cliff, plug this in, divided by acceleration of gravity, and square root all of that, what I get is that the time is equal to 1.41 seconds for this person to fall 10 meters. It doesn't sound like a lot, but it's because gravity's really big on this planet. So finally, we are going to get the dx equals vx times t, and that's pretty straightforward. So she's going to move forward 5 meters every second. She's going to do it for 1.41 seconds, and all that turns out to be about 7.1 meters. Okay, that's example number 1. It's pretty standard. So you're going to rock this. Let's go ahead and do one more, and we'll check it out. So here's an actual image of a cliff diver. This is a famous place in Acapulco called the Cordoba Cliffs. So this is true. These things are 22 meters tall. So as you're reading this, you just think, okay, well, that's a dy. It's the height. How fast does he have to leap horizontally in order to clear the rocks below? So it's a little bit different question. What they're actually asking us to solve for is what does the vx have to be so that you clear these rocks down here? I guess you can't just jump. Oh yeah, obviously. If you step off of this, you'll get croaked. Remember these. dy is 22 meters. They give us the dx. That's the sideways distance where this person's going to land if they go the minimum safe speed. So let's go ahead and just jump on that one and check it out. So vx is what we're trying to solve for. dy, they give us 22 meters. This one down here, dx equals 6 meters. And we're going to go equation shopping. So the first one that we can use is, again, it's this one right here. We always have the g. In this case, we have the dy, so we can get busy and figure out this t. So t equals square root of 2 dy's over g. So 2 times 22 meters. What's going to be neat about this one is if you go ahead and plug all this in, you'll notice that we get like 2.1 seconds. So this person jumped from over twice as high as the last question. The time it takes them to hit the water, not nearly as big as twice the time. It's not even close to twice the time. That's because they get going faster and faster as they fall, right? The y motion is just the motion of a falling object. So we can take that 2.1 seconds and then take our first equation right here. And let's go, oops, sorry. First equation was this one, dx equals vx times t, that I didn't write down. And let's go ahead and snag that. So vx equals dx over t, and we'll solve it. So dx is going to be 6 meters, 2.1 seconds, and all that boils down to the minimum speed is 2.8 or so meters per second. That's doable with just a couple good steps. So you take a couple good steps and you leap, and you'll be going that fast, and pretty much anybody can do it. But hitting the water the right way, that's a whole different skill. That's it. So those are the guts of what you need. Take good notes, bring your questions to class, and look forward to seeing you real soon. Have a great day. Bye-bye.